Today I'll be talking about work and heat. This will be in 3 parts. Let's talk about work. Work, in physics you learned that work was force times displacement, or you could say is force times distance. But more exactly, work is the integral of a force working through a displacement. So if you were to plot force versus displacement and going from one place or one state to another, and you took this wiggly path, the work would be the integral of this function in going from 1 to 2, or it would be the area under the curve. So we can say that work is a force acting through a displacement, and we could also say that work is the area under the curve. Since it's the area under the curve, we can see that work depends on the path that is taken, so we say that work is path dependent. Now, one important thing to note about work is the sign convention. And we say that work done by a system is positive, and work done on a system is negative. It's important that you be aware of this because back around the late 1970s, they changed the sign convention. But we're going with work done by a system is positive, so when a system expands, you get positive work. Work done on a system is negative, so when a system is compressed, you'll get negative work. Now, in some textbooks, they will say that work done by a system is work out, and they'll say that work done on a system is work in, but we're going to go with by and on. Now, in talking about work, we're also going to be looking at different types of differentials. So when you see us taking a derivative and you see a differential, the shape of the letter D is actually important. If you see just the letter D, that is an exact differential. What that means is the result depends, or the function depends, only on the initial and final states. So if I were to have a function, box, and I were to take the integral from state 1 to state 2 of d box, it would be box at state 1 at state 2 minus box at state 1, or we could say that it is delta box. Now, if we look at the squiggly d, or a lowercase delta, that indicates an inexact differential. That's a function that depends on path. So if I were to have another function, and I would say del, or squiggly d, del circle cross, and if I were to evaluate that integral from state 1 to state 2, since it's path dependent, I would just say that it's circle cross from state 1 to state 2. We don't use delta here because we're not looking at the initial and the final state and taking the difference. We're indicating that this is a path function. Now, in some textbooks, you'll see the 1 and 2 on the same side, the two different states on the same side. That's not 12. That's circle square and going from state 1 to state 2. Sometimes you'll see this other d, which is a partial differential, and we'll look at that later, actually much later. But if you remember, we're looking at how a function changes with respect to one variable when we hold all the other variables constant. But let's get back to work. We said that work depends on path, so work is an inexact differential. So if I'm looking at the work and going from state 1 to state 2, that would be the integral of del W from state 1 to state 2, and that would just be the work in going from state 1 to state 2. You'll notice there's no delta there because the work is path dependent. In looking at work, the SI units would be joules, and we know that 1 joule is 1 Newton meter, or it's 1 kilogram meter squared over second squared. The English units for work will be the foot-pound force. Now, we can talk about power. Power is W dot. It's the time derivative of work. Remember, when you see a dot, that is a temporal or a time differential. When you see a prime, usually that's a spatial differential. W dot is just work over time, or it's del W dt. The SI units for work will be the watt, where 1 watt is 1 joule per second, which is equal to 1 Newton meter per second, or 1 kilogram meters squared over seconds to the third power. The English units for power would be the horsepower. And the power of 1 horse, or 1 horsepower, is 550 foot-pound forces per second. Now, sometimes we'll use something else, which is specific work. That's a lowercase w. That is work per unit mass. That lowercase w is defined as work over mass. It will have units of kilojoules. It'll have units of joules per kilogram, kilojoules per kilogram, or foot-pound forces per mass pound, or pound mass. So we've talked about some work. Let's look at work in thermodynamic processes. Because in thermo, we're looking at converting work into heat and heat into work. So we're going to look at work done on or by liquids and gases. So we spent some time learning the thermodynamic properties and how to find them for these liquids and gases. So now we're going to look at the work done by these liquids and gases. So we're going to consider a gas in a piston cylinder assembly. So we've got our cylinder and we've got our piston. We'll just say that the pressure acting on the gas inside is P. We remember that that could be atmospheric pressure, and pressure due to the mass of the piston. We've got some gas inside, and the piston is at a height L above the bottom of the cylinder, and we can say that the area of the bottom of the cylinder is A. The pressure would just be the force of the piston over area, or we could say the force acting on that gas is pressure times area. Now what we're going to do is displace this piston by a distance dl. It's just a smidge, or it could be some indefinite amount, L, that the piston has moved up. If we look at the work done by the gas in moving this piston up, it'll be del W. And we said that that would just be the force times the distance. So to be the force that the piston is exerting times the distance that the piston has moved, dl. But if you remember, force is pressure times area, so we get that the work, del W, is pressure times area times dl. But looking at the area of the piston times the height that the piston has displaced, or the area of the bottom of the cylinder, times the height that the piston has displaced, we see that AdL is actually the change in volume, dV, or the amount that the volume has changed. So we get that del W is equal to PdV. So going with that, del W is equal to PdV. The work in going from state 1 to state 2 would be the integral of del W, which would be the integral of PdV evaluated from state 1 to state 2. So what this shows us now is work would be the area under the process on a PV plot. So taking a pressure volume plot, if I go from state 1 to state 2 on this PV plot, whatever path I take, the area under that path would be the work for the process. The next, we'll be looking at how we would solve some problems or the equations we'll use to calculate work.